Welcome, everyone. Thank you for joining us today as we host BLINQ Networks for a webinar on how to transition smoothly to CBRS and LTE. My name is Seth McElrath. I'm an account manager here at DoubleRadius. And our guest speaker today from BLINQ is Dan Stewart. Dan has over 30 years of experience as a wireless systems and network engineer, and he currently serves as BLINQ's senior sales engineer. Before I turn it over to Dan, just a couple of housekeeping items. If you have any questions throughout the presentation, please enter them into the questions box so we can get them answered. And when the webinar is over, please take a minute to provide your feedback on our quick survey. And with that, let's jump right in. I'll hand it over now to Dan from BLINQ to get us started.
Great. Good morning, afternoon, whatever the case may be for you. My name is Dan Stewart. As he said, I'm a senior systems engineer for BLINQ Networks. I was a U.S. Navy veteran. I did 6 years in Washington, D.C., buried in a black vault for naval intelligence. So much for, seeing the world. It took a career in wireless networking for me to actually see the world. I've been in the wireless industry, like you said, for 30 years. I've worked with most of the technologies, including pre-Wi-Fi, proprietary wireless LANs, point-to-point and point-to-multipoint, and, of course, standards-based technologies like the LTE. I have been working with the LTE for about 8 years solid, which included stints with Ericsson and Telrad. So that's a little bit about me. We're going to dig right in. We're going to go right to the topics here. I think that's the plan as soon as I get this thing to move. There we go. So this is going to be our general agenda. We're going to talk about CBRS. We're going to talk about how BLINQ makes life easier. And we're going to talk about the portfolio that we have. So this is just general. We're going to go into some detail on certain things that are important you may or may not know about. But I hope that you hang in there and we'll go ahead and get started. So in the license spectrum, the challenges are typically license cost and availability. It's not unusual for a Tier 1 or Tier 2 to purchase a license in a geographical area and then only deploy the absolute minimum in order to keep their license. This is extraordinarily inefficient, especially when other wireless ISPs who have customers and want to deploy can't use that license simply because they're sitting on the license. So that's been quite honestly the biggest issue that's driven us to shared spectrum. It's like the spectrum's been kidnapped and then left the island. So in the unlicensed spectrum, in the 2.4 and the 5 gig bands, enterprise technologies have been the workhorses for many years. So, but there's challenges with the technology, and it's been ongoing. Cell edge, reliability, ongoing interference issues, pretty much all those things really tend to drive a little bit crazy some of the wireless ISPs that are deploying, especially when Joe's Pizza and Internet decides that they're going to set up a wireless ISP. So they have no experience. They go out there and they set up and start deploying. And next thing you know, your network, which you have plenty of experience and understanding of, starts having interference issues. So those are things that you have to deal with in the unlicensed spectrum. So what we're going to talk about a little bit more today is the shared spectrum. Shared spectrum basically solves these problems by implementing a SAS sharing model. So simply put, the spectrum sharing is a use it or lose it tiered model, and it allows for spectrum availability at the same time. It provides protection to a limited amount of spectrum priority license holders. We're going to talk about that in depth in a few slides. So the 2.5 gigahertz band, basically known as band 41, that's basically 249 to 2690 megahertz. It's about 194, close to 200 megahertz wide. It's the most commonly used license band for fixed wireless LAN markets and the TDD. But licenses are divided into much smaller bandwidth per licensee. So it's not like somebody owns the whole 200 megahertz. It has the best propagation in the TDD spectrum, and because it's licensed, it has very high predictability, little to no interference. So it's definitely been the right band, but the biggest problem, again, has been the cost of acquiring the spectrum, and the majority of the spectrum where you want to use it is already owned. So in the 5 gigahertz spectrum, this has the widest bandwidth, approximately 555 megahertz of bandwidth available. Most of the fixed wireless LAN vendors in this market are all proprietary solutions, and much of that technology is surrounding avoiding or mitigating interference issues. To make matters worse, the EIRP restrictions brings propagation issues. There's no guarantee of availability, and as I said, Joe's Pizza Shop and internet company can ruin your day very quickly. If you've been in the wireless business and you've been dealing in the 5 gigahertz band, you know what I'm talking about. So recently, the FCC opened up the 3.5 gigahertz band, or CBRS band. It's 150 megahertz wide, and it's presented a set of specifications that would allow both a licensed and unlicensed use in a tiered approach. The high ERP transit power allows us to mitigate against the propagation challenges. And of course, the OnGo Alliance, which has adopted LTE as a specification. LTE is a well-known standards-based technology and works really well in situations of non-line of sight. Now, let me preface that as when I say non-line of sight, I don't mean a forest full of trees. It's pretty amazing when I find out that customers, are putting up LTE on a tower that's 90 feet high and the trees are 85 feet tall, and they're concerned that they can't get through a mile and a half of trees. So, reality is that, it's non-line of sight, but non-line of sight does have its restrictions. It's a phenomenal technology, though, that supports it much better than any of the proprietary technologies in the 5 gigahertz band. So the Wireless Innovation Forum formed a committee to facilitate the implementation of spectrum sharing and rulemaking. It changed its name recently to OnGo. So you're going to hear a lot about OnGo. OnGo allows industry and government bodies to collaborate to implement a common, efficient, and well-functioning ecosystem around the technology. The dynamic spectrum sharing system has been formulated under the Spectrum Access System called the SAS, SAS. And you're going to hear that a lot in this terminology here. In Citizens Broadband Radio Service, that's CBRS, CBRS has been introduced for WiMAX, LTE compatible bands, primarily targeting small cell applications complementing primary mobile networks. The CBRS band fits right in between bands 42 and 43, as you can see. Whoops, too far. It's basically 150 megahertz wide. The band is structured to provide semi-exclusive use of the upper 50 megahertz, 3650 to 3750, to GAA, or General Authorized Access. Now, what I mean by semi is that federal incumbents, which are primarily the U.S. Navy and some fixed satellite areas, have priority to utilize the entire band, and so they can occupy the upper band. However, PALs are not issued in the upper band. So PALs are priority access licenses. The lower 100 megahertz of the CBRS band allows for 70 megahertz of this band to be auctioned off to these PALs. Each auction is for a single 10 megahertz channel, and a single PAL can own up to 40 megahertz of that spectrum. Okay, but they have to bid for this, right? See, so what does that leave? What does that leave the GAA users? The GAA users have a minimum of 80 megahertz, right? So they've got 50 plus that 30, so they've got 80 megahertz of bandwidth to play with, which is really nice. So it really helps out the guy that can't afford those expensive licenses that can deploy in those areas. So a little bit about some more of these slides. The user priority, I've already talked a little bit about that, but the federal incumbents, those are the guys that can basically transmit anywhere, and if you're transmitting while they're transmitting, the SAS will shut you down. It'll either lower your transmit power or move you to a different available frequency. It does all this on a priority basis, right? So the priority access licenses, they have to deal with federal incumbents as well, just like the GAA user. The only unique thing is that if they own that license, then the GAA will actually be forced to move off the license or off the channel that they own, or reduce their transmit power, again, based on what the staff decides. So it's important to note that this is a use it or lose it scenario, right? So somebody can't come out there, buy PAL licenses. And by the way, PAL licenses are issued by county. So every county in the U.S. has auctions for this. So what that means is if they buy it and they're not using it, the GAA can come in and utilize it. So again, it's a use it or lose it kind of scenario, which is very unique and very much more efficient than those license bands that we talked about. So the dynamic protection areas, I already kind of talked about that, and basically it's mostly coastal areas used by the federal government, typically U.S. Navy and some fixed satellite systems. Typically, the U.S. Navy utilizes a fairly narrow band of the spectrum, 5 to 15 megahertz, and they're on, typically just a few hours at a time. There's no guarantee of this, but that's what is typical. So we're going to continue on. We're going to talk a little bit more about the functional CBRS architecture and, those pieces involved. Before I get started, I want to reiterate that CBRS, the On-Go Alliance for CBRS, has adopted the LTE standard for communication. Okay, so there's a reason why they did this. Obviously, to standardize, anybody can utilize it. But the one thing I want to point, those of you that know a little bit about LTE, you'll notice in this functional CBRS architecture, there's not a single LTE block in here, because CBRS handles just the transmission, when the radio can transmit, what power the transmit can be, and what channel it can be on. Everything else is handled independently with the LTE architecture, okay? So the spectrum access system basically manages and assigns spectrum on an as-needed basis. The SAS determines the available frequencies at a given geographical location and then assigns them to the CBS. It registers and authenticates the identification information and its location. It protects, again, what I said, federal incumbents and priority access licensees from harmful interference from any kind of general authorized access user. Okay, there's two types of CBSD. There's a category A, which is a low power CBSD that meets the requirements. It has to meet the requirements of the general CBSD, but its ERP restrictions are 30 dBm, and and the height above average terrain is limited to 6 meters. And then the category B type is basically a higher output power CBSD. Again, it has to meet all the requirements that the FCC proposes for a CBSD. These have to be deployed outdoors, and they're required to be professionally installed by a CPI. CPI is a certified installer. Okay, the maximum ERP for CBSD is 47 dBm, which is 50 watts per 10 megahertz channel bandwidth. Most of your outdoor CPEs and eNodeBs fall into this category. Then there's a third category that we really haven't talked about, which is the end user device. These don't require any kind of registration with the SAS, and they're very low profile, 23 dBm or less. As far as the ESCs, they're called environmental sensing capabilities, and they're used to detect federal frequency use in the entire band. The ESCs basically communicate this information about detected frequencies to a SAS, and then the SAS makes the determination if those frequencies that are being utilized are interfering with the incumbents. So typically, where you see the ESCs deployed are all around the coast. Literally, Federated Wireless was one of the first companies to actually deploy a full set all the way around the entire coastal areas of the United States. And again, they're responsible for reporting back and helping the SAS to make determinations on what channels and output power should be used. There's a thing called a domain proxy. It's basically a managing intermediary, if you will, for CBSDs. It's not a requirement. In fact, in Release 1 of the CBRS specifications, the domain proxy's primary function is to aggregate and report the protocol messages from CBSDs towards the SAS and then vice versa. The informing incumbents, they're basically federal inland radars that inform the SAS when they would like to transmit. And there's a industry-defined DoD-approved portals that the SAS uses to communicate and protects those inland radars from lower-tier users. And finally, you have the FCC database, basically controlled by the FCC and NTIA, that contains information required for the proper operation of the SAS. So a little bit about CBRS, where we're at today. January 2020, the FCC gave CBRS the nod for full commercial deployment. And so we are in the midst right now of operators deploying and early deployments, connecting with the SAS and working out the issues involved, that sort of thing. This month, I believe, July 23rd, is when the auctions actually begin. Sorry, second. There's seven PALs, so 70 megahertz of bandwidth available for the licensed area. So total wide, that means 22,631 PALs nationwide. The PALs consist, I've already talked about this, 10 megahertz. They're unpaired channels, and the licensees will be able to aggregate up to 4 of those PALs in any licensed area. So far as of June 23rd, they've received 348 applications to participate. We've got Tier 1, Tier 2, and 3, and we've got wireless ISPs that have also said they are going to join in. And something that you may not be aware of, but utility spaces like Chevron, San Diego Gas and Electric, Corning, John Deere, Texas A&M, they're all looking at PAL licenses to deploy private LTE. Remember, this is not just a wireless ISP play, and that's really important when you're looking as a integrator looking to deploy. You don't need to be looking just there. In fact, a lot of the new technologies supporting mobile vehicle, that sort of thing, sensors, that sort of thing, Internet of Things, if you will, really opens this up wide, and of course they can play in that arena. Private LTE use cases outside of fixed wireless access, we've already talked about that. So imagine hospitals, airports, hotels, manufacturing, municipalities, ports, railroads, public venues, stadiums. So there's just a plethora of unique situations where private LTE can actually deploy. There's critical communications for security and operations teams. We actually see customers now deploying cell on wheels, CALs, for emergency use. And we're going to talk a little bit about how that capability is deployed with our products. We're unique in that we can be deployed very, very quickly. Remote vehicle guidance, point of sale, you name it. There's just a whole lot of fixed wireless access opportunities. If you're not sure about them, you want to learn some more, please contact BLINQ, and we can share with you some of these in more detail, especially, and we're all about supporting you in your efforts. So let's talk a little bit about the BLINQ Networks product line. Before we do so, we want to talk a little bit about the LTE architecture. So the primary LTE components, you got the user equipment, which is the UEs. You got the UMTS, which is called the EU-TRAN, if you will. Basically, it's the radio access network. That's what encompasses all the radio, right? And then you have what's called the EPC, or the Evolved Packet Core. This is where all the magic takes place internally to convert all these signaling and data planes to actually support internet access for those UEs. Keep in mind, the UEs, these are low power, but we also have CPEs, customer premise equipment, that are higher power. They're Class B devices, and you could look at them. They're not called UEs, but you could look at them as another connection back to that eNode B. BLINQ Networks actually sells CPEs, and that's kind of like what's going on there. So hopefully, if you want to learn more, just let me know. We've got other webinars that we can do with it's a little bit more of a deeper dive into the LTE architecture, but this is just the general. So it's really important to note that BLINQ is a standards-based LTE, right? So what are the benefits of the standard, right? One of the problems that the non-standard LTE, or the non-standard non-LTE products have is dealing with non-line of sight challenges, right? Mostly because of the power. The power is pretty restricted in the 5 gigahertz band, and so that deals with distances. Basically, you have much more attenuation, trees blocking the line of sight. Low power signals get scattered and absorbed by those leaves, and the modulation of the signal gets so low that it's totally useless. The truth is those people who can beat the non-line of sight and the associated attenuation by using the LTE are the ones that win in this marketplace. The design, obviously standards-based, is unlike Wi-Fi. Even though Wi-Fi is standards-based, a lot of proprietary wireless or fixed wireless access vendors have promoted this as a Wi-Fi solution. It was never intended as a outdoor solution. In the face of foliage and that sort of thing, it really has issues. There's LTE basically does a much better job. In fact, it holds about 7 dB advantage over Wi-Fi on a per modulation basis. So this is a massive benefit of LTE. A couple of the other ones are price, right? So why is price much better in a standards-based? Well, simply because it's standards-based. Example is we're all carrying around those LTE-enabled phones, right? You may be on one right now, right? So in just a few short years, it's just basically displaced all the other mobile technology. Okay, so as a result of that, as a result of demand, the cost of these phones are dropping considerably. It's not to say that you can't pay $900 for a phone still, but you can pay $39 for an LTE phone that works just as good as one of those $900 phones when it comes to LTE communication. The other great thing is the innovation, right? So as we have this influx of LTE devices, it results in a really massive continuing investment by all the parties to bring new services and build new devices, right? So there's over $1 billion invested annually in LTE and R&D, and it's a standard. So every new leap is, and by the way, those leaps are always backwards compatible, which means no single vendor can put your entire CapEx environment at risk like it can in a proprietary network, right? So we've already talked about spectrum. I'm not going to go on about that, but those are just some of the reasons why you want to be doing standards-based LTE. So what are the key technology propositions from BLINQ? Basically, we have a really strong uplink and robust link adaptation for foliage and wind. I live out in the Colorado area, and I have been very fortunate to be part of the team testing our CPE, and it just continues to amaze me what the non-line of sight capabilities are. It's proving itself day over day to be the leader in CPE equipment use. So as far as our base station, we're going to talk about that a little bit more. We have a multi-sector antenna system that actually allows you to adjust where you want to provide coverage to. And this is electronic adjustment, so you don't have to go up and deploy a different antenna. And you can add capacity as you need. So this is very unique. Again, it's all OnGo certified. We have a X300, we have this X300 product, X300i product, and then we have another product called the FW600 that's going to offer up to 10 gigabits per cell site. So imagine that. That's just phenomenal. So we're going to continue on here. We're going to talk a little bit about the FW300i. This is our flagship right now product line. It's an all-in-one integrated unit. What you see here is actually what you deploy here. That unit, as you see here up on the upper left, that's actually 2 units sitting back to back, which provides a 360-degree coverage area. Now, the reality is that in that box, there's actually 3 eNode Bs that are operational, okay? And those 3 eNode Bs also have high gain antennas. We're at the maximum ERP that you can transmit. So imagine that. That box is all your antennas, your GPS, everything all in one box. You don't have to deal with those external radio cables. You don't have to deal with, my GPS getting damaged, that sort of thing. Everything is involved. It is included in the one box. Even included it as an option is the EPC. You can literally set up a network and operate it and do local offload to the internet right from that unit. That's phenomenal. That's to me, that's a game changer, and it's really impressive. I've already talked about most of this. Again, 50 dBm per carrier per sector. The 2x2 MIMO performance. We can support up to 96 users per sector, so that's 288 users per FWA 300, right? It's got 3 sectors, so 3 times 96. Now, the reality is you're not going to deploy 96 users per sector in a fixed wireless access environment providing internet to home. That's just not going to happen because the bandwidth has to be divided among that number of users. But where we do see this happening is environments such as what we talked about, private LTE environments, where low throughput requirements, but a huge number of those devices. Imagine, let's say, at an airport, at a tarmac, where every device needs to be tracked and dealt with. So you could easily have hundreds of those devices in a cell site connected. So keep that in mind. So this is just an example of that software-defined radio that I talked about. In the lower right-hand corner, what we're dealing with there, what we're talking about there is 6 sectors, each doing 1 CC. 1 CC is a component carrier, so 1 20 megahertz channel. You can change all of this and manipulate these. For an example, you see the next configuration over, the 3 CC to the left, the next configuration where you've got a 3 CC channel, a 2 CC channel, and a 1 CC channel. And of course, there's going to be gaps in those areas. But if you plan this carefully, you can see where the obvious capabilities come in, that you can basically cover just the areas where you want to have coverage. A lot of times, wireless ISPs or fixed wireless access users that are deploying 360 degrees, just a small part of that, maybe 3 or 4 or 5 sectors are actually being used. Well, that sector, that area that's not being used, you can add capacity to the sectors that are being used. You can double up the carrier so it can go to 2 CC, or you can have a carrier overlay, which allows another frequency to overlay that same area for capacity. So it's just a phenomenally well-designed unit. The X300i, it's a tri-sector. It's meant to go up on light posts or be roof-mounted. It supports up to 500 megabits aggregate capacity. As you look at that kind of triangle there, each one of those are 60-degree or 120-degree sectors that are covering 360-degree coverage. This is working really well in metropolitan areas where you want to mount this up on a light pole and provide access. My testing that I've done has been phenomenal. We did some testing in Minneapolis where we're getting 80 megabits per second at a half a mile to a mile away. So very, very impressive. And again, it does have that unique functionality to aim. If you have a sector, if you have one of those sectors, one of those 3 sectors that are not being used, fewer customers, where you can roll it over to the other sector and add additional capacity with just a change in the configuration, the software configuration. So we're going to talk a little bit about the BLINQ EPC solutions, right? So as I said, we have an embedded EPC. The embedded EPC is really the workhorse for the super fast, easy deployment option. Okay, this is the kind of thing where you might put up, let's say, at a mobile home park or smaller areas that don't have a huge requirement for the number of eNodeBs, but you want a local data offload. Let's say you bring the internet. I'm going to bring internet right to a campground. Let's use that as an example. I'm going to bring my backhaul internet right to that unit, and literally it's got an EPC embedded in it, so you can do local data offload right from there. All your MZ, the EKI, and the OPC functions are all inputted in a simple format. This is required if you have deployed LTE at all. You know what I'm talking about. This basically the SIM card, if you will. So the shortcoming of this is you can't roam. Okay, you can't have a device roam from one embedded EPC to another embedded EPC, and we don't support IPv6. As far as the centralized EPC, this is something that supports really large environments, and this is server-based. We've talked about this. Sorry. So we've talked about this. Basically, it's sitting out at the core, and you can scale this from 100 users to 100,000 or more, and it fully supports mobility as well. But this is where you have a wireless ISP where you might have 25, 50 to 100 eNodeBs in a particular area, and you want to support that at the central core. And of course, we support multiple EPCs for backup and redundancy, that sort of thing. As far as our CPEs, we have two flavors of CPEs. We have a Cat6 and a Cat12 device. The category basically defines, if you will, mostly the peak throughput. So you can look at what the capabilities are there. We're talking about supporting up to 440 megabits per second in a 3CC environment, which is pretty darn impressive. I myself have seen 2CC work with multi-beam farming delivering 280, 300 megabits per second straight from the CPU. That's UDP throughput. So very, very impressive. Again, reach out to us if you're more interested in this. We also have what's coming up is a antenna pointing tool. A lot of wireless ISPs forget that changing the azimuth and just pointing it in the right direction is not the best solution. You really need to fine-tune it, because fine-tuning it, just additional 3 dB, can have a huge impact over what that performance is. And the other thing, too, that a lot of people forget is azimuth, or elevation, right? How many of you guys actually tell your tech guys when they're installing to make sure that you point it up a certain number of degrees? A lot of times that's lost, and you can gain anywhere from 3 to 5 dB just by pointing it in the right elevation. So this pointing tool app that we have basically supports that sort of thing and provides very, very detailed configuration, not configuration, but very, very detailed analysis of that installation, where you can keep a history of what each CPE and how it was installed. And finally, we have our network management system. The network management system is called NetLiNQ. The network management system is basically a full EMS. It supports REST northbound interfaces. It aggregates really well with the rest of the network. You can manage and configure the network as well as keep it historical accuracy as to what's going on in the network, see reports that are set. At any rate, I think that's about it. I'd be more than happy to talk with you individually. You can reach me at dan.stewart@blinknetworks.com. I welcome your questions and greatly appreciate what you've allowed me to talk through. And if there's any questions, we'll take those at this time.
All right, thank you, Dan. We do have some questions, and I will go through those. Just one moment. How long does an operator have to utilize the assigned spectrum once the SAS gives it out?
Indefinitely, right? So, you know, it will only be changed if the SAS finds that there's a need to change the frequency or the transmit power as a result of the PAL or the federal incumbent that wants to utilize that band. So when you use it, it's there as long as you want to keep it.
Okay. With 96 users on the FW300i, how's the latency? And along with that, what's the bandwidth capacity that would be divided?
Right. So that's important, and I think I filled in that information. Maybe perhaps somebody may have asked that question before I filled in a little bit more detail about that. What we're talking about here is, on a 1cc environment, we're talking about 110 megabits down and maybe 10 megabits up. And that's all got to be shared amongst all the CPEs. That's in a 1cc environment. As you go up and you include 2cc and you go to 256 QAM or 64 QAM on the upload, all of that increases, but that bandwidth has to be divided by that number of devices on the sector, right? So that's the reason why, preface this, before you guys, have an absolute heart attack about that 96 users, understand that private LTE is a real thing right now. We've got a lot of opportunities that are out there that are doing things like autonomous vehicle monitoring. Imagine farming and being able to, and this is happening all the time, being able to support automated vehicles in the farming world, if you will, that have really low throughput requirements. And so that's the reason why we say up to 96 users. We can support up to 96 users. Real gut check is that if we're talking about 96 users on a single sector that are all the typical home, which is looking, at using 25 to 30 megabits or more, just for a small family, if you put 96 on there, nobody would get anything. That's just because it's it's a simple capacity equation, right? And again, we talk about this in some of our other webinars. We talk about oversubscription rates and that sort of thing. So hopefully that answered your question. I was not trying to propose that you deploy 96 users per sector, fixed wireless access environment.
I think we have one more question here. Are the eNodeB used as a spectrum analyzer for the SAS?
That's actually an option supported by the SAS providers. BLINQ does not do that right now. It's pretty much a proprietary solution right now. It's basically an add-on. It's that I know of. I don't believe it's supported by any of the eNodeB manufacturers at this point right now. Eventually, it will become a solid part of it. But again, it's optional, and basically what it does is, just as you said, it acts as an ESC sensor as well for the rest of the networks where an ESC potentially may not be able to cover.
Okay, it looks like that's a wrap. As we close out, please take a minute to fill out the survey that will pop up on your screen. And thanks again for joining us today. Stay safe, and we will see you next time.
Thank you all.